All right, this is our first just-in-time lecture, and it will cover both hybridization and bonding for section 11.3, talking about valence bond theory. All right, so as usual, I'm going to cover the most often missed questions, so those questions that had a less than 80% success rate. Our first one talks about when two hydrogen atoms first approach each other, which is this area right here. What is true of the 1s electrons? And what I was hoping everyone would catch on is that the spins are independent of one another. If the spins are independent, that means that we can have these two atoms coming in and they can both be spin up, or we can have these two atoms coming in, and we can have a spin up and a spin down. It doesn't matter because they're independent of one another. Now, as soon as they move in close enough to form a bond, this changes. They have to become spin paired. So if one of these is spin up, then it has to flip to go spin down, because now we're talking about combining them in a single orbital. Now, if after I explain these slides you still have questions, feel free to post those questions on Piazza so we can get them answered before you attempt the quiz. All right, so on this slide, we were talking about the formation of H2O, and we talked about how if, say we had the px and the py orbitals on oxygen, trying to combine with the 1s orbitals on two hydrogens, how if they're coming in without any sort of adjustments, they're going to have this 90-degree bond angle according to valence bond theory. So right there, valence bond theory. All right, so because VBT predicts 90 degrees, but the observed bond angles are 105 degrees. Remember, the tetrahedral, the ideal is 109.5 degrees, but because we have these two lone pairs pushing this bond angle shut, we observe a 105-degree bond angle according to valence shell electron pair repulsion theory. So here we have a big disconnect where valence bond theory is not working for us. That's why we have to adjust it and invoke hybridized orbitals to make it work. Okay, what is the best way to describe the energies of the 2s and 2p atomic orbitals on carbon? Okay, so the key point here, these are the atomic orbitals, and the atomic orbitals, recall, the 2s orbital is going to be lower in energy. All right, and the 2p, they're going to be the same energy, but it's going to be higher than the 2s. So we would say that the 2p orbitals are higher in energy than the 2s orbital. It's not until we get to our hybrid orbitals that we see all four of these sp3 hybridized orbitals having the same energy. All right, on this slide, the best way to describe the sp3 orbitals on carbon is that they have the same energy. That's what degenerate means. Degenerate means same energy. All right, on this particular slide, this question showed up in both hybridization and bonding play posits, and it was how many electron domains are around carbon in C2H4, so our ethyne. And if we count, we've got 1, 2, 3 electron groups around C2H4 each carbon. Because we have those 3 electron groups, we know we need 3 hybrid orbitals to be formed. All right, how many atomic orbitals are required to make 3 hybridized orbitals? It's important to realize that the number of atomic orbitals that you put in are going to equal the number of hybrid orbitals that you get out. So if you need 3 hybridized orbitals, you better put in 3 atomic orbitals. So B was the best answer there. All right, so here's the just-in-time lecture for the second play posit over valence bond theory. How many atomic or unhybridized orbitals are found on each carbon in ethyne C2H4? Recall that to make our ethyne molecule, we had 3 electron groups, and 3 electron groups require 3 hybridized orbitals. So we see that we need that sp2 hybridization. So because we have S, a P, and a P, notice that one of these p orbitals gets left out. So it stays purple in this diagram. So these 3 are hybridized. This one is not. And so our p orbital shows up unchanged at the end. So the correct answer is 1p orbital. All right, how many atomic or unhybridized orbitals are found on each carbon in ethyne C2H2? Same deal here. Each carbon has 2 electron groups around it. So that means we need 2 hybrid orbitals. So we only have to put in 1 s and 1 p. Because we only have to put in 1 s and 1 p to get our 2 hybrid orbitals, that means that we have 2 p orbitals, and these 2 p orbitals remain completely unchanged. All right, are any atomic or unhybridized orbitals left on the central atom? This one makes you stop and really think a minute. The first thing we want to do is look at how many electron groups are around the central carbon. We have 1, 2, 3 electron groups. Hi, toesies. And that means that we need 3 hybrid orbitals. And so we're going to have to add 1 s orbital plus 2 p orbitals to get sp2. Because there are 3 p orbitals available, that means that we're going to have 1 p atomic orbital left, because in this grand scheme of things, if we're talking about, we've got an s and we've got 3 p orbitals, if one of these gets left out because we only need an sp2 hybrid, then we still have that 1 p atomic orbital left. All right, so this was a challenging question. Acetylsalicylic acid contains how many sigma and pi bonds? All right, so the key to this is that each single bond equals 1 sigma, and each double bond equals 1 sigma and 1 pi bond. All right, so if we go back and count the single sigma bonds, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So 21 sigma bonds. If we go back and count the pi bonds, everywhere we have a double bond, we're going to also have a pi bond. So we have 1, 2, 3, 4, 5 pi bonds. All right, so that concludes this just-in-time lecture. Again, if you have questions, please post those to Piazza and get them answered before you tackle the quiz. Thank you.